the previous videos, we have discussed about the basis of selecting the tendon profile, which can be done in reference to the bending moment diagram of the member, both in terms of the magnitude of the eccentricity and in terms of the positions of the steel tendon. It was mentioned that the sudden changes in terms of the curvature will lead to significant frictional loss. In order to prevent excessive frictional loss, normally we make the turnings to be smoother, and there will be a transitions of the curve so that the gradient will later be adjusted to the intended gradient in accordance to the tendon profile. It was also mentioned that there are cases that special arrangement may be required in order to avoid the difficulty in terms of the applications of the tendon profile. In these videos, we're going to discuss some of these special arrangements. The slide here represents different types of the conditions where different types of the tendon profile is being used. First, let us look at this prismatic beam. It is basically the basic tendon configurations, which is normally used for the short slab and lightly loaded beam, and it doesn't require a significant amplitude of the curvature. One of the advantages of using this system is it only involves simple form work. However, due to the turning of the curvature, there will be high intermediate losses due to the friction. The tendon profile normally follows the bending moment diagram, and there will be large angular changes, which is changing the directions of the tendon over the span. Ultimately, it will end up like a waveform of the tendon profile. The more span it is, there will be more wave of the tendon profile. In order to minimize the frictional loss, tensioning may be done at the both ends of the member. This reduces the effective length of the calculations for the frictional loss, which subsequently will reduce the frictional loss along the member. The second type of the member is haunch beam. The meaning of haunch beam means that the effective section of the beam varies along the spans. At some support, there will be a larger effective depth of the section. This leads to a higher degree of effective depth of the section, and due to the changing depth of the sections, the positions of the central axis will also vary along the length. The hidden line here represents the central axis, and there are two types of the haunch beam here in terms of the tendon profile. The first one is the continuous tendon with the cap cable as shown here. The second one is with the tendon profile of different positions along the member. This type of the beam is mainly used for the long span and heavy loads, where there is a necessity in order to increase the degree of eccentricity, especially at the regions of high negative moment. Therefore, normally the regions at the support have a higher degree of effective depth, and there will be a shallow cross-sections at the midspan of the region. This mechanism plays around with the changings of the central axis, so that with small fluctuations of the tendon profile can still lead to a significant increase of the effective eccentricity. You know that higher degree of eccentricity will lead to higher degree of moment caused by the prestressing member. This will give you extra prestressing effects at the high negative moment regions. You know that the frictional forces increase with the magnitude of these fluctuations of the tendon profile. If you wish to minimize the frictional loss, ideally you will have the tendon profiles to be in a straight line. Although the tendon profile is in the straight line, because of the changing positions of the centroid axis, there will be effective eccentricity between the central axis and the positions of the tendon. This can still lead to the effects of the prestressing caused by the eccentricity. And you know that for normal conditions, we would like the members to be in the positions of the negative eccentricity. This is so that it generates resistance to counteract this negative moment at the intermediate supports. This can be done by having this cap cable, which at the end of the day, it will lead to the equivalent centroid of the tendons to be halfway between the cap cable and also the straight tendon, and that distance from the centroid of the area with the centroid of the sections, it will be the effective eccentricity of the positions. Through this, we can foresee that the amount of frictional loss can be minimized, and this kind of design is advantageous for long span with heavy loops, which you require a higher degree of eccentricity to generate sufficient resistance due to the prestressing force. There is another ways of construction here. The tendon profile here is similar to this tendon profile, except that you have a concern in terms of the high degree of frictional loss. You know that if you want to use this kind of beam, the only way for you to reduce the frictional loss is by having the tensioning process done at both ends of the tendon. In the case that you have much more longer span, due to the increasing numbers of the turning of the curvature, the frictional loss is still high, then you could consider to use this segmental beam construction. That means the beam is stressed segment by segment, which is later to be ensured continuity at these cavities. These segments are stressed together using the coupler to achieve continuity, where these couplers and the hydraulic jacks are allocated within the cavities. These cavities provide rooms for you to work for the pre-stressing operations. After you have done pre-stressing, the cavity can later be filled with concrete, cement grout or other suitable component in order to cover the tendons. By doing this, you will have much more shorter effective length for the frictional loss, and this will subsequently reduce the frictional loss. Next, we look at another construction method, which is known as the cantilever construction, or it is referred as the balanced cantilever constructions. You see this kind of constructions normally for the applications of the bridges, where there will be segments of precast members being installed one by one in the balanced manner. The meanings of balanced cantilever is you will have to install these two panels first before you proceed with the next two. The process will continue, and at the same time, at the other pier, we'll do the similar process, and the construction of bridge will complete when both sides meet at the midspan. Now that you have precast members to be installed together with the pier, you will need to post-tension the tendon here so that the members stay attached to the piers. To prevent undesired bending moment during the constructions, we will install the two members together so that the final resultant is still vertical force acting along the neutral axis of the pier. Or we can install the segment alternatively beside the piers in order to minimize the effective moment caused by the eccentricity of the center of gravity of the bridge relative to the central axis of the pier. This will minimize the turning moments acting on the pier during the construction. After you have post-tension the member and this member will behave as one element, you will proceed with post-tensioning for the following segment. And now you will have another tendons connecting both segments. The same process proceed for the next segment until the bridge meet at midspan of both piers. This kind of construction methods normally are without major forcework system. That means the amount of the formwork can be minimized, and it is normally applied for the large span structures such as the bridges that spanning the highway, rivers and valleys. And the precast elements are positioned alternatively on either side of the pier and stressed against the previous placed element. During the constructions, the structures is used to sustain the erection force and also the construction loads as a simple cantilevers. And after the constructions, the structures is resisting the service load as a continuous haunch girdles. Next, we look into the porter frame. You know that the porter frame with pre-stressing forces is not widely used, which personally I can't recall if I see any of this kind of structure anywhere. Nevertheless, it is still applicable. It is especially required when you require a large space within the porter frame, which is nearly not achievable by a typical reinforced concrete structure. Due to the perpendicular arrangements of the beams and the columns, the members are usually stressed separately. The tendon will cross each other at the corners of the frame, and there will be anchors at the end and also at the top face of the frame. If you analyze the porter frame carefully, you will see negative moments at the joint between the beams and columns. This will behave as is the conditions of the intermediate support, which normally you will require the negative eccentricity. You will require the positive eccentricity at the midspan and negative eccentricity at the end span. Therefore, normally the tendon here is provided with negative eccentricity at the end span and positive eccentricity at the midspan. You also see that the size of the column here varies along the height. The purpose here is to generate the eccentricity by adjusting its central axis of the column so that it becomes negative eccentricity at the end of the column.